Okay, so we talk about the numerical solution of differential equations in using MATLAB. Okay, so for this, I will take this example from the book. Okay, y prime is equal to 4e power 0.8x minus 0.5y. From x is equal to 0 to x is equal to 4, and we will solve it numerically. I will only illustrate, I will not use do the algorithm for these different methods. We have done a few algorithms before, and then using the similar approaches, and then also the using the some of the pseudocode given in the book, we can write these algorithms. So I will only talk about the function, the MATLAB function for uh, the solution of the numerical differential, for the solution of the differential equation, ordinary differential equations. Okay, so let me show you this. So as I have told that I will take this example, which is this one. Y prime is equal to 4 e power 0.8x minus 0.5y. So we will solve it numerically using MATLAB. So for this, for any solution of the ordinary differential equation in the MATLAB, you will first go to the editor, okay? And in the editor, you will write the format of the function. So it will be like that. So you will write, we'll start with function, and then you will give the name of the function, and then the variable name. So in this case, our function is given by y prime like this. So it is, we can say it as y prime by p. Okay, y prime we can represent by yp, or we can also represent as dy dx over here in my MATLAB. So I represent it as yp. Yp means y prime equal to, now I will give the name of the function. So the name of the function over here, I can give any. So we can say that this was example, sorry, this was example 25.5. Okay, so I can say it as example 25.5. Example ex mp exmp example. Okay, example 25.5. Okay, we don't use 0.5, that otherwise it will be an invalid variable name in Excel. So example 25.5, and then parentheses, and here I will represent the independent and the dependent variables. So independent and the dependent variables are, in this example, x is the independent variable, y is the dependent variable. Okay, as it is dy over dx, so x and y. Okay, so I will put x and y, and then parenthesis closed, and then I will write it, write the formula for yp in the body of this function. Okay, yp will be equal to what was that formula? 4 exponent 0.58x. Okay, 4 exponent 0.8x. So 4 times exponent 0.8 times x minus 0.5 times y. It was 0.5. So 4 into exponent 0.8x minus 0.5 times y. Okay. And then put a semicolon, and then you will end it. Okay. In this way, I will define the function for the derivative. So when we want to define the function for the derivative, you will start with function keyword, and then you will have to give a variable name. So in this case, since we are using a y prime, so we can say it as yp, or you can also represent it as dy dx or any other suitable name. And then here you will write the function name. Function name in this case is example 255. So it will be represented by this. And the function name, then we will, inside of the parentheses, we have to provide the variables, independent and the dependent variables. And in this case, yp function was 4 exponent 0.8x minus 0.5y. In the body of the function, we will define the function, and then we will end it. So after that, you will save it. So if it is a function, the function name should be saved as the name of the function which we have already defined. So it will be saved as example 255. It will be saved. So this is one step. The next step will be performed in the command window in the MATLAB. So in the command window, first we will give the range of values. So the range of values are from x is equal to 0 to x is equal to 4. Okay, so we will give the range of values. So the range of values are x is equal to 0 to x is equal to 4. So I can say it as x range is equal to 0, comma 4. Okay, so it is a matrix, one row, two column matrix, 0, comma 4. And then semicolon. The next thing which we need to input is the initial condition. So the initial condition was that at x is equal to 0, y is equal to 2. So for x is equal to 0, y is equal to 2. So the initial condition is so we will give represent the initial condition y 0 is equal to 2. Okay, so y0 is just the name and 2 is the value. Okay, so after that, now we will apply the built-in ordinary differential equation function in MATLAB to obtain the results. Okay, so for obtaining the results will be in the form of independent and the dependent variable values. So the independent variable in this case we represent by x, dependent variable we represent by y. Okay, so this is the output of the ODE functions, and the ODE function over here we will use ordinary differential equation 4.5 in the MATLAB. So ODE 4.5 is a MATLAB function for the solution of the numerical solution of the ordinary differential equation. So 4.5 over here means that it uses the fourth and fifth order Runge-Kutta method. Fourth and fifth order Runge-Kutta method, fourth or fifth order Runge-Kutta method for the solution of the equation with the adaptation. Similarly, there are some other functions as well, maybe 2, 3 1, 2 as well. But for most general applications, we will use the ODE 4-5 equation, as it gives us the generally suitable, accurate results. Okay, so can you hear me well? I did not ask before.
Yes, we can
Yes.
hear you.
And you can also see the MATLAB. Okay.
Yeah, yeah.
Okay, so for ODE 4-5, the format is we will start from the at. Okay, simple at, and then here you will put the function name. So function name is example, at example 255. Okay, and then comma, and then I will then you will provide the x range of values, so which you already defined, and then we will provide the initial value of y. So y 0 we will provide, and then we will close the parenthesis. We will put a semicolon, and then I will hit enter, and it is giving me error because I made some typing error over here. It is example, ex example. Okay, so now I will hit enter. So now when I hit enter, so the command has executed, and here you can see that in the workplace, the certain x and y values have been generated. Okay, certain x and y values have been generated. So for these will be the these are the solutions of these values. Okay, solution values. So in order to visualize these solution, we can plot these x and y values. So plot x comma y values. Okay, and maybe I can plot them as circular markers. Okay, circular markers in red color. I will put OR. O will show the circular markers, R is for red color. And then I will hit enter. So this will give us the, this will give me the solution. Okay. So these are the solution points. Okay. So this gives the solution. So how well this solution, how well this solution is matches with the real solution. So this we can also see. So for this, what we can do is, we all, in this example, we already know the analytical solution. This is the analytical solution. So we can also plot this analytical solution over this, and then we can see the difference, how how well it matches it. So for this, for plotting this analytical solution, so if we also need the values of x and y. So what I can do is I can take the analytical values and represent by xx. Okay, I can take a sample of the xx values, and then I can use a uniformly distributed xx values from 0 to 4. So this linspace 0 to 4 command will produce 100 equally distributed values of x between 0 and 4. And then for the analytical solution, maybe I can represent it by yy is equal to. So what was the analytical solution? So I have to type it over here. Analytical solution was 4 divided by 1.3. Okay, so I will go back to over here. So it will be 4 divided by 1.3. 1.3. multiplied by exponent. It was exponent, multiplied by exponent 0.8x. Okay, exponent 0.8x. 0.8 times x, but in this case it's not x, it is xx. Okay, and minus exponent minus 0.5 times xx. You see, minus 0.5 xx, and then it's bracket closed, and then plus 2 over here. 2. Okay. So this was the bracket for exponent, and this is the bracket for this multiplication, and plus 2 times exponent minus 0.5 times xx. So it was plus 2 exponent minus 0.5 xx 2 times. Okay, so in this way I have represented this xx value. So now I can plot xx and yy as well. So in order to plot it on the same graph, I will put a command hold on, so that after that I will put the plot command. Plot xx against yy. So by default it will be plot as a line, and now I will hit enter. So this plot xx and yy will be the analytical solution. And now I will hit enter, and I will go back to this over here. So now you can see that these circular markers are the solution from the ordinary differential equation numerical solution, whereas this smooth line is the analytical solution. And then as you can see that from this graph, both of these values are both these solutions are matching very well. Okay, maybe you can just zoom it to see the solution. So even in the zoom, these solutions are matching very well over here. I can further zoom it. Yeah, so in this case, the solutions are almost exactly matching. Okay, actually exactly matching the solutions. So this means that
I have a question.
yes.
So the ODE 45 does not show like the stopping parameters, like number of iterations when the approximations were made. Yes.
Yes, ODE 45 include will not show this details. It will produce the results for the range which we need to provide. Okay, so ODE
And
we need to provide the range. Okay, so it will produce the results between these two ranges.
okay. So but what about like the estimation, the estimated error? Like, does it have a certain threshold to like stop its calculations?
Yeah, it may have some, but that is just internally into that
Okay.
equation. Okay, so in this case, we have seen the use of ODE 45 function of MATLAB for this numerical solution of the differential equation, ordinary differential equation. So we remember that you have to adopt this type of procedure. So first we have to define the function, define the differential equation as into a function. And then we have to invoke that function into this ODE 45 to find the solution. Okay, so in this case, what we can see is that the ODE 45 in this format is giving us a range of values. But what if we want to find some particular value for the
Sorry,
function?
I have a question.
Yes.
So we cannot invoke the ODE45 function like just as not by invoking the other function that I didn't, but as like straight away. We cannot do it. Yes.
Yes, we
Okay.
have to do like this. So we have to first store it as a function, and then we can use it. So this is the standard method.
Okay.
Okay, and yes, so so in this case, as we have seen that ODE 45 has given us the range of values. So for example, X range values and Y range values. What if we want some particular values of X and Y? So for example, what is the value of the function at X is equal to 1? So for this, what we can do is we can use the same command like this, but instead of in storing it as a two component output, we can store it as a one component output. So maybe we can say store it as okay, SOL, okay, and SOL. So in this case, we got some error, right? Unrecognized function or variable. Oh, okay. So yeah, there was this spelling mistake. Example. Yeah. So in this way, in this case, these y values. That means the structure. In this case, not the x and y values, but the structure of the solution has been stored over here. Okay. The structure of the solution has been stored over here. And now if we want to, if I want to find the value of this solution at say x is equal to 1, so I can find this value. So maybe I can say that for x is equal to 1, I want to know the value of y. So I say that its value is y1. Okay. Its value is y1. And then for this, I will use another MATLAB function. That MATLAB function will be called as deval. Okay. Deval. Okay. Deval for evaluate. Deval. I will evaluate what sol, which is the actually its type is the structure. Okay. It is the solution structure. And then at what value I will give the value. Say if I want x is equal to 1, so what is the value? And then I will hit enter. So I will get the value as 6.1946. Okay, at x is equal to 1. So maybe we can see it from here. Yeah, so at x is equal to 1, this value will be about 6.1946. But here we have numerically obtained this value. Maybe we can also evaluate it. So for example, we say, I say xx is equal to 1, okay? And now if xx is equal to 1, then what will be yy? So yy, because yy is the original value, right? So original value can be calculated from xx value. So yy will be equal. Oh, no. What is that? Okay, so yy. Mm, yes, yy is here. And yy is equal to oh no, I did not actually calculate it. These are the previous values of yy. Okay, so I should apply this yy, yeah, this one now, and it's okay. I will apply again without this semicolon, and now I will get this value of y 6.1946, which is the same as 6 as before. Okay, maybe if I use the format long, and now I say what is the value of y1. Y1 is this, and what is the value of yy? Yy is this. Yeah, you see that in format long there is some difference, right? So this is the value which we calculated from ODE 45, and this is the analytical value. But the difference is after maybe fourth and fifth digit. So this means that although the solution is quite close, but it is not the exact solution. There is still some difference between these two solutions, between these two numerical and the analytical solutions. Okay, so is it clear this second point, like this solution structure? Right?
Could you repeat the algorithm? So we first divide the as this
Yeah. So okay.
x1 and x1.
Yeah, in the first I plotted the x and y values. In the second case, I just equate this ODE. So for example, this one.
Oh, okay.
Yeah, here it will provide two sets of outputs. But here, if I just put it like as a single variable, SOL, A, B, C, whatever, so it is giving us a structure of the solution. So this structure of the solution can be evaluated at different values. So I just took, for example, a value of x is equal to 1. I found the value of 6.1946. So when I compared this value of 6.1946 with the analytical solution, which was also 6.1946. But when I formatted it to a longer version, so this is 6.194632, and this is 6.194613. So there is some difference, okay? But up to
Okay.
at least 5 decimal places, both values are same. So the
I have a
conclusion,
question.
yes.
So this why did the yy will like show us the all the values from
Oh,
does it contain the values from 2 to
oh, here?
yeah, from
You
2
mean
to
here?
4 to yeah, yeah.
Oh, here, because I did a mistake because I did not evaluated the new value of yy. I just
Oh, okay.
displayed the old values of yy from previous case. So that's why by mistake all the
Oh,
values were
okay, okay.
displayed. Okay, so even in this case, we can see that, but we cannot see where it was. But here we have the values, the calculated values corresponding to the equally distributed values of x and y, equally distributed values of x. Okay, so this is that one example for that, for this case. So for one, it was 6.19466314, right? So the same which we got from here, true value. And this was the true value, right? And this is the value, the very close value we also got from this numerical solution. Okay, so another thing is that, well, this ODE 45 we can use for a system of equations as well. So for example, if we have a system of equations like this, instead of, if we have instead of one equation, we have two equations, then how we can use it? So for example, one equation is dy1 over dx is equal to minus 0.5 y1, and the other equation is dy2 over dx is equal to this equation. Okay, so in this case you can see that there is one independent variable which is x, but there are two dependent variables y1 and y2. Okay, y1 and y2. So how we can find the numerical solution for this system of ordinary differential equations? But here for in the book, it has been shown for the Euler's method. But a more complete example has been shown in the 27th chapter. So maybe we can see from here. Yeah, here. So yeah, it's the same example, but what has been shown over here. So similar example. So in this case, we have the system of two differential equations. There is not just one differential equation. There are a system of two differential equations. So, but the thing is that the independent variable is t is the same. The dependent variables are x and y are different. So we can use the same. We can use MATLAB to find the solution. So for this, I go to the MATLAB. Maybe I close this chart and just clear everything. Clear CLC. Okay. And even I close this editor window. Now I open the new editor window. So in this case, we will start from the function, and the function name we will give at y prime. Okay, y prime is equal to what is this function name? What is this function name? This is example 27.9. Okay, so I can give it as a function name example 27.9. Example 27.9, and here independent variable is t, dependent variables are x and y. But in this case, we will take x and y as both y. Okay, we will not put it like x comma y over here. We will just represent x and y as both as y. Okay, both as y. So in this case, then x will be replaced by y parenthesis 1 and y will be replaced by y parenthesis 2. Okay, so let me show you what does it mean. So yp is equal to example 279 ty. So now we will define yp. Sorry, yp is equal to here you will see that it's actually already written over here. So yp is equal to this 1.2. Here you can see that there is this close bracket. So these close brackets are over here are for showing the two equations, because there is only not just one equation but the two equations, and then these two equations have been separated by semicolons. So that means this is the first row and then that will be the second row. So it will be a 2 by 1 matrix yp in this case, okay, representing these two equations. So in this, but since we are only using y as a dependent variable, so we will represent these two dependent variables x and y by y parenthesis 1 for x and y parenthesis 2 for y. Okay, so in this way it will work out. So so the equation is 1.2x minus 0.6xy. Okay, so the first equation is 1.2x. So it is 1.2 times x. But since we are representing x by y, number 1, and minus 2xy. So x is represented by y 1 times y 2. Okay, and then semicolon. So 1.2x minus 2xy, right? Yeah, 1.2x minus 0.6xy. Okay, not 2xy. So it is 0.6xy. Okay, so the next equation after this semicolon, we will represent as minus 0.8y plus 0.3xy. So minus 0.8 times y. So y is represented by y2 and plus 0.3 xy. Okay, plus 0.3 xy times x. X is represented by y1 times y2. Then bracket close. So, and then we will put semicolon, and then we will end it, and then we will save this function. So this function will be saved as yeah, actually there is a mistake. Fun function, yeah, function. Now it should save as, it will save as example 279 and then save it. So now because for this system of equations, so where x is equal to 2, then x is equal to, for at t is equal to 0, x was 2, y is equal to 1. So the uh, uh, initial values are 2 and 1 for y, and the range of values are t to 0. So we will first define the span, that is the range of values. So t span is equal to 0 to 20. So we have to integrate it from 0 to 20. Okay. So T span is equal to 0, 20, and the initial values are, that is the y is 0, y is 0. Yeah, y0 values are 2 and 1, because for t is equal to 0, x was 2, y was 1. Okay, so these are the initial values. Okay, so where is this? So y0 is represented by 2, 1, 2, 1, 2, 1. So now I can apply the solver. So in this case, we can this example has applied another solver. Okay, but we can apply any other 4, 5 as well. So 2, 3 is another solver. Okay, ODE. So it can be applied like this as well. So for example, so it is this one. Here the name, our name of the function is example 279. Okay, 279, and then it's t span and y is 0. And then if I execute this command, so it is giving us the answers. Okay, so it is by the TODE, and maybe I can plot it. Plot T against Y. So I get this result. So what does this result show? So one of the curve will be for dx over dy. The other curve will be for uh, so one of the curve will be x against t, and the other of the curve will be y against t, because in this case you can see that the solution is dx over dt, dy over dt. So we will find two solutions, t against x and t against y. Okay, so therefore there will be two curves. Okay, so this is the solution that you will obtain. Yeah, it's the same solution. So in this way, then what you can see, what you have seen over here is that you can use the system of equations, system of ordinary differential equations. You can use in this way. Okay, that means in this case the only difference, the difference between is from the previous case when we use only one equation, is that in this case for the system of equations we have to input all these equations into one matrix format. In the span we will also represent by the matrix format, and the initial condition we will also include it into the matrix format, and then we can apply the ODE solver, any of the ODE solver, 2, 3, or 4, 5. So let's see in this case, if we apply this ODE solver 4, 5, what will be the solution? So instead of, so then I can represent it by TT, YY, and then if I use 4, 5, And then maybe I can use the add example 279, and then I do it. So I got these values. So hold on, and now I plot TT against YY. Okay, and then let's see what we get, or maybe I can plot it with the yellow circles or orange circles, or red circles. Okay, circle and then black circles. Okay, and then let's plot it. So let me see the graph. Here I can see that, yeah, both 2, 3, in this case, both 2, 3, and 4, 5 are giving quite matching results. So for example, these circles are represented by the ODE 4, 5. These curves, that is the lines, are represented by ODE 2, 3. So you can see that, sorry, here, if I just, yeah, so both values quite match with each other. Yeah, there is little bit difference over here. You see, there is a difference between these 2, 3, and 4, 5. When we zoom it out, so there is some difference. So we can use any of these solvers. Okay, so that's what I wanted to explain today. So I hope it is understandable to you. So do you have any questions?